Our next speaker is going to be Dr. Kishith Mal. He's a postdoctoral research associate at the Center for Integrated Systems in Aerospace at Purdue University. He obtained his PhD and master's from the School of Aeronautics and Astronautics at Purdue University and was a postdoctoral fellow in Aerospace University and Aerospace Engineering in Auburn University in 2019. And previously, he completed his BTech in Mechanical Engineering at the JSSATE Noida in India, and then worked for a year at Infosys Technologies as a computer systems engineer. And his research interests lie in the areas of optimal control theory, atmospheric flight mechanics, and explainable AI and human-class Mars missions. He'll be presenting his paper with a variety of authors. I won't list all of the names, but you can see the link to the paper in the chat, which is on mission engineering and design using real-time strategy games and explainable AI approach. So go ahead, Dr. Mal, whenever you're ready.
Yeah, namaste and good afternoon to all. Thank you, Mark, for a very kind introduction. And in the next 30 minutes or so, I'm going to share with you what my team has done in 13 pages. So there is a lot of information, but what the intent here is to share high-level detail of the work that we have done. We have, as you can see, submitted to Journal of Mechanical Design and luckily got accepted for that. The title of the paper has been Mission Engineering and Design Using Real-Time Strategy Games and Explainable AI Approach. Now you see a long list of authors, some whom like me enjoy playing games for a living, but on a serious note, actually it's not moving, just a moment, yeah. Our team has been looking at the mission design problem. And what happens in that is that we try to identify or pick those missions or engagements that helps us to maximize certain objective. For example, a probability to win a contest. And in this mission design problem or mission engineering and design challenge, one thing is that it involves a large and complex design spaces with evolving and dynamic mission environments. So that makes it extremely challenging in order to solve these problems. So there are a lot of simulation environments that have been built in order to address the challenges posed by mission engineering and design, MEAD. Some of those are ASME, which is Advanced Framework for Simulation and Integration and Mission Software. So that is ASME for you. Then there is Command, Flashpoint campaigns, and whatnot. But these are actually very complicated simulation tools that are available. And some of those have been used by US Air Force, Department of Defense, DARPA, and such. But this project that was given to us was by DARPA called the Game Breaker program. And what our team came up with is learning to game break methodology, which is what we have devised and which I'm going to present on the same. And in that, what we looked at is these RTS games or real-time strategy games, which many of us enjoy playing for leisure. But here we have been using that in order to understand the dynamics of the game and how to use that and take it out to the real world. So how these RTS games help us is that they abstract or show a mission execution as a game played between different agents which have competing objectives. So like I said, we came up with this methodology or a framework where we have these different layers and different tools comprising artificial intelligence, explainable AI, Monte Carlo dropout networks for uncertainty quantification and whatnot. So there are a lot of complex things that are in that, which I'm going to share in subsequent slides. In that, one key thing that we used or a concept called game balance, and what we defined balance is like a game is balanced when all the players that are involved in the game, they have equal chance of winning that contest or that game, given an environment for the game, like whatever environment we have for the game, given that environment, if everyone has the same chance for winning that contest. One thing that we took out of this definition is the skill factor, which is the ability of a player to select certain strategy or certain sequence of events. So we took that out because it was getting more complicated and our sponsor didn't want to include the skill factor. They just wanted to see, just based on an environment, how does it play out and what the game balance is. So the framework that we eventually devised is very efficient for mission design because it's able to build a surrogate model for the mission environment, which I'll be showcasing shortly. So this is the three-layered approach that we came up with, and our team devised this having three different layers. One is the player layer, then there is a tournament layer, and then there is a game breaker layer. So all these layers, they talk to each other, and there is a lot of exchange of information. The player layer, actually, as you can see, there are self-play games. So in order to get the skill factor out, what we started doing is we have a bot player, and that bot player plays against itself. So that's a self-play game. So we started using that so that we don't have any skill involved, only the game environment. And you can see there are certain types of bots that we used. Some of them are deterministic in nature, which means they have a set strategy. They are not going to change it if we play it more and more times. But there are certain which actually change their strategy based on the different runs. So one of them is the portfolio AI, which we have used in this study for more complex results and for more interesting results. Now, when we have these players, we make them play different tournaments of games. And for that, we use something called design of experiments. And with that, we have a whole tournament set, which generates huge amount of data. That all data goes into and feeds into this game breaker layer. And there we have all these artificial intelligent models, which are able to predict who is going to win the game. Is it player 0 or player 1 in our case? And then once we have these predictions, we want to make sense of those predictions, like why is player 0 winning and not player 1 winning, is because there is certain thing going on in the environment or with the players. So for that, we use the tool Explainable AI, and we use a particular tool called SHAP for that. And once we have these Shapley values or the results, then we are able to gain more sense of these predictions. And based on that, we are able to close the design loop, and we are able to guide the design of experiments again to run like what is more important and what the design space should be explored and we should focus more on. So those kind of things this whole setup is able to address. Now, this is the game that we chose, and why we chose this micro RTS game is because it is one of the easiest games to understand. And what we wanted to show is that there is this 3-layered framework, and then it works. So in order to showcase some results in an easy manner to the community, we thought of choosing this simplest game, which is built for AI research. And then just like any other RTS games, it has like 2 players with the light unit, heavy unit, and there are range units which are not used in our study. There are workers, resources, barrack spaces. So it is very similar to any of the games that we play, in which there is an objective of you want to win, you have more units, you want to damage the other units of the player, you want to build more resources over time, and the one who has more point at the end of the game wins. So that is the objective of this game. And then this is a slightly like the snapshot or a zoomed in version of the 2 other layers, which is the tournament layer and the game breaker layer, and how they talk to each other. So like I mentioned, that we have these tournaments between different, like the player who is playing against itself. We have a lot of these different games for different settings. For that, we use design of experiments. And then we have these like 2 different types of data. One is like the image snapshot of the game, and then also scalar things like number of units of the players, the health of the units and all that. And then we use all that information in order to train a very complicated convolutional neural network here in this case, along with dense branches, because we have 2 different types of data. And then once we have that model trained, we get the predictions out of that, and we are able to get a good enough accuracy for our model. So once we have that information, we also pass that information through the explainable AI model, which tells us that we have the sanity check through that. Is our model behaving correctly? And if it is behaving correctly, why is one player performing better than the other? Or why are both players like in a balanced situation? So those kind of things we are able to unfold and understand. And then you can see a lot of these feedback loops coming in, because they inform each other and tell that like, okay, these are the features that are important. We need to focus on these, and we need to change our settings so that we can build our model even better, right? The accuracy can go higher if we can do that. So that is the snapshot of the game breaker layer and the tournament layer and how they talk to each other. One other thing that I want the audience to take away from this is that this is a very generic framework. So what I'm presenting here is for a very simple game, micro RTS, but in reality, we have used the same concept and tried to solve a much more challenging game environment called StarCraft 2. Some of you might have played it. that is way more complicated than this micro RTS, and involves like very complicated bots and a lot of more features, and the design space is extremely complicated. But still, using the same framework, we just made some small changes, and we were able to tailor it for more complicated RTS games. And the same concept can be used for other domains as well. So that's the beauty of this framework, is that it's very generic. And like I shared here, convolutional neural network or SHAP, you can always go around and change these things based on your needs. So that is another good thing about this framework. And then I've been talking about the design of experiments. So in that, we have different attributes for either the player or for the game environment that I've been talking about. So those things you are able to change. They have certain values like a minimum or a maximum. Here, for example, the player I have fixed, so there is no minimum or maximum. But for certain other things, there are some ranges. So you can go and change around those things. We have used something called Latin hypercube sampling, which is a smarter way to use these, the values and to set up these tournaments instead of going the n factorial way and making like changing every single thing. So that we have used successfully. And we have 5,000 games that we generated using this design of experiments. And each game we played around 5 times because we used Portfolio AI bot, which is more stochastic in nature. So total of 25,000 input games we had. And at the bottom, you will see some of the other features that have been used. One is the terrain feature that we introduced, so that there are some blocks or there are some challenges for the player to move around and its units to move around. And there is a certain region where the player 0 or the player 1 can spawn. So that is this 5 by 5 block. This map has been used as 16 by 16 because it had good enough space to traverse and to give us complex and interesting enough results. So that is why we have used this. And here is something about our model. The inputs that are generated using the tournament layer. What we have done is we had those 25,000 games, and for each of the games, we captured 30 game frames because otherwise there are just tons of them. So we had to reduce the size so that it's computationally feasible to train this model. And then we had 2 different types of data coming in. Like I said, there is a spatial data or a geographic data, and there is a non-geographic data. Both of them feed into the model. And then out of that, we get certain game balance metric, which is useful for us. So here we have chosen something very simple, is which player is going to win? Is it player 0 or player 1? So that probability it tells. So that is in short the model that we have used. And this is a more detailed snapshot of the model that we have generated. You can see there are tons of blocks here, and there are all types of layers because we have different types of data used. So we had to use different types of layers, one to address the image data and other to address the non-spatial data. And then we concatenated them and merged them together in order to finally have the predictions out. So one other good thing is you can see we use something called Monte Carlo dropout method, which helps us to make the model less sensitive to the inputs, because what it does is it keeps changing the connections between the neurons. It switches it on and off. So there is some uncertainty involved. And that's why we are able to see if the model is more sensitive to certain inputs and if it is not. So we using this, we are able to gain sense of what time the model is able to predict more accurately or more with more confidence, and at what times it is not. And there are certain times in the game where it is expected that the model should not be able to predict with high certainty, because even we don't know what's going on. Only when the game passes to a more advanced stage, we come to know like, okay, player 0 is going to definitely win, or player 1 is going to definitely win, or it's going to be neither, like it's going to be a draw. This is one of the very cool things that we used, and primarily I've been assigned this task of getting SHAP into play. This is one of the explainable AI tools, which is very popular nowadays. It merges around 7 different explanation methods that are out there. And the objective has been to, like for different types of AI models, we can just use the SHAP tool and we are able to explain the predictions, like why certain things are happening. And since you know that we are using games, and these games involve either player features or environment features, So we care about the importance of these features, like which feature is more important and what we need to pay more attention to. So here, if you see, we usually have some training data that feeds into a CNN model, and then we get some prediction. But what the SHAP does is it maps this training data into either the feature is contributing to something, some useful output, or it is not. So it's between 0 and 1. And then that information goes into the explanation model. And what we get out of that is Shapley value. So these Shapley values, they actually tell that what is the contribution of a particular feature. Is it actually adding to the win of a player, or is it actually taking away from the win of a player? For example, if the health of a player is very good, that is actually helping it to win the situation. If the player has more number of units, it's going to help the player to win the situation. So things like that, this is able to uncover through the Shapley values. Another thing that the SHAP does is it tells us whether your model is correct or not at the first place. If you are getting very random answers, that means more likely or not, your model itself is incorrect. So in our case, our model turned out to be good enough, but then we were able to uncover some very interesting scenarios out of it. Also, it helps in something called optimal learning, which we have not been able to implement in this study. But the idea is to, smartly explore the design space in an optimal way, instead of, searching the whole big design space and investing a lot of computational resources on the same. Moving on to the results, some of the interesting results that we found is the very first one actually started our team because we posed a game situation in which everything was kept symmetric. A player is playing against itself. That means both the players are same. Everything else, like the number of units, the resources, the situation, the position, the location, everything is the same. Even then, we saw that there is an initial imbalance in the scenario. And then we thought, like, why would that be the case? Then we found out that even if you keep everything the same, there is an inherent imbalance. This is because of the movement order and the path planning logic implementation, because at certain time there may be conflict, and then in order to resolve that, one player will be given an advantage over the other. So that has to be resolved. We cannot keep sitting there and then both players are in a stalemate situation. So the designers have designed that in that way. And our team actually got in touch with the maker of the game, Professor Antonon, and he also agreed that movement order is actually the reason for this imbalance, and path planning falls prey to that. This is another interesting result you see, like for one of the games that we had. And this was again given to us by our sponsors, DARPA. So here what you see is written perturbation 1, which is one of the perturbations they gave to us. And in this, what you see is that this game is highly balanced at the start. Like this is the prediction. It's basically 0.5 for a long time. And then one of the players start winning and the other starts losing. So for this particular game, we said like, okay, things are balanced. And what we need is to identify some of the key game features. For example, the position, base location, the number of units, or the damage rate, or the health of these units. So those were identified as some of the main units. And you can also see the SHAP values here. One other thing I would like to tell is how we read these SHAP plots is that whatever is in red, that is contributing to the outcome. It is positively affecting the win of a player. And here it's the opposite. If it's a blue, that means it's taking away from the outcome. So you can see health of player 0 is negatively impacting and health of player 1 is positively impacting the situation at this particular game frame, which is the first game frame. So for this, what we did is we identify the game features which are most important, and then we altered them a bit. And we tried to see like, okay, if we change certain things about this game, and we know intuitively like, okay, if we decrease the health of the player, then it should start losing the game. And this is what you start seeing, like player 0 starts losing the game, player 1 starts winning the game. Before that, it was actually like a mixed contest. But as soon as we made this change, things will start happening a different way. So here the predictions align with whatever is observed. Similarly, when we increase the damage rate that a player can do, it starts actually winning the contest. Player 0 starts winning the contest here. But the third thing that we try to do is we change the location of player 0 to a different location, which we thought is more favorable for player 0. But then the model actually predicted in a counterintuitive manner that is because some of the things our team also did not understand very well is like when we change the position, there is also a relative change in the location of the resources, and there is also a change in the relative location with the other player. So there is a lot of like this complicated coupling of lot of other things that is going on, which we were not able to capture in our model, and that requires us to feed more training data and such. So that was the interesting thing that we found out with these 3 perturbations.
Dr.
And you can
Moffat,
see,
could you please conclude your talk soon so that we can move on to the other speakers? Thank you.
Yeah, sure thing. Thank you. So basically, what I have to tell on this slide is that you can see these SHAP values, they seem to be similar, but at the end, there is a small change or there is a small differential because of which you can see one player winning and the other player not. So it is that small change in the SHAP values, which is important to be noted on this slide. And then we just have to design our experiments based on all these features, and we need to pay more attention to these things which the SHAP has uncovered. So that helps us in closing the design loop. And at the end, the key takeaways from this are that we saw an initial imbalance, and whenever you are designing a game, you should pay attention to this initial imbalance, because even if you think everything is balanced, it may not be the case. Secondly, our team came up with a very generalizable and scalable methodology that includes CNN and SHAP and things like that, which predicts and explains the game balance for any game state and efficiently enables us to navigate through the large design space, which is one of the challenges for the mission engineering and design domain. And then we were able to incorporate uncertainty quantification and able to close the loop by identifying some of these relevant features. So thank you so much for your time. And thanks, Mark, for helping conduct this session. Thank you.
Thank you. Okay. As a reminder, you can place any questions for the speaker in the chat. Okay. All right, so now we'll move on to our last speaker for today.